When we talk about quantum algorithms, it's easy to get lost in all the complex equations and abstract math. But what if I told you we could understand a really powerful optimization technique just by thinking about it like a simple game, like hopping pieces around a board? Well, that's exactly what we're going to do.
So, picture this. We're playing a simple board game, but this isn't just any old game. The rules here are actually going to show us how to crack some incredibly tough real-world problems. And the secret? It's all in how the pieces are allowed to move.
All right, so let's break this down from the ground up. We're going to call our game particle hopping. And yeah, the rules are super simple, but the idea behind it? It's the foundation for a whole new class of really powerful quantum algorithms.
First things first, let's define our pieces and our board. In this game, a particle is really just a qubit that's in the one state. You can just think of it as a filled spot on the board. And a site, that's just a qubit in the zero state. It's an empty spot just waiting for a particle to land on it.
Okay, so what makes this game so special are its rules, and they are very strict. Rule number 1, you start with a set number of particles, and that's it. Rule 2, the only thing you can do is have a particle hop to an empty spot right next to it. And rule 3, and this is the big one, the absolute golden rule, the total number of particles can never, ever change. You can't add them, you can't take them away, the count is locked. So, okay, we've got a game with rules, but what's the point, right? Well, the goal here isn't just to move particles around for fun. It's to find the one single best arrangement of those particles on the board, the arrangement that solves our specific challenge. And this right here connects directly to a huge number of real-world optimization problems. Things like logistics, network design, you name it. They're what we call constrained problems. It's kind of like saying in a delivery route problem, each city can only have one truck. If you send 2 trucks or none at all, the solution is invalid. It breaks the rules. That's a constrained problem.
Which brings us to the million-dollar question. If our problem demands that we never, ever change the number of particles, how on earth do we build a quantum algorithm that actually respects that constraint? We need a tool that's been designed to play our very specific game.
Now, a go-to method for these kinds of problems is the Quantum Approximate Optimization Algorithm, or QAOA. And if you look in its standard toolkit, you'll find something called the X-Mixer. The only problem? For the game we're trying to play, it's completely the wrong tool for the job. And here's why it's such a bad fit. This standard X-Mixer works by just flipping individual qubits, turning a 0 into a 1 or a 1 into a 0. In our game's language, that means it's constantly creating and destroying particles out of thin air. It's just popping them in and out of existence, which means it spends almost all of its time exploring configurations that are totally illegal, totally invalid. So, because this X-Mixer is wasting so much time wandering around this massive space of illegal moves, the actual search for the best solution becomes incredibly inefficient. It's like we've asked it to find a needle in a haystack, but it's spending all its time searching in a completely different county. And this is where the hero of our story comes in. If the X-Mixer is the wrong tool, we just need to find the right one. And that perfect tool, the one that was practically built for this, is called the XY Mixer. It was designed from the ground up to play the particle hopping game. Now, this equation right here, the XY Mixer Hamiltonian, think of it as the rule book for our game, just written in the language of physics. Don't worry about all the simples. What's important is what it does. It's designed to only look at pairs of sites, and if it sees a pair with one particle and one empty space, its only move is to make them swap. That's it. It's an engine that is hardwired to only allow hopping. And get this isn't just some clever trick we came up with for an algorithm. Physicists have known for decades that this exact mathematical structure describes how certain quantum particles literally hop around in real-world materials, like quantum magnets. This is a great way to actually see it. This diagram comes from the physics of quantum magnets, and it basically shows that the most natural, lowest energy thing for these little particle-like excitations to do is to just hop from one spot to the next. Our algorithm isn't inventing a new rule. It's literally borrowing a fundamental behavior from nature itself. So let's just quickly recap what makes this tool so perfect. First, the XY Mixer is excitation preserving. Fancy words for it keeps the particle count the same. It does this by basically acting like a swap gate, just trading places. And this guarantees that the algorithm's entire search is confined only to valid solutions, what physicists call the feasible subspace. No more wasted time. So we've got the right tool for the job. But what's the actual payoff?
Why does all this matter?
Well, as we're about to see, taking this tailored approach gives us a truly massive advantage in performance.
Using the XY mixer inside QAOA isn't just a minor tweak. It creates a whole new approach. It's called Constraint-Enhanced QAOA, or CQAOA for short. It's basically a framework built entirely around the idea of respecting the problem's rules from the very beginning.
And here it is. Here's the payoff. For certain types of problems, their research has proven that using this particle hopping XY mixer gives you an exponential speed up over the standard approach. And just to be crystal clear, that doesn't just mean faster. It means it's in a completely different league of performance.
I mean, to put that number into perspective, just look at this chart. The search efficiency of CQOA, the one playing our game, is exponentially higher than the generic one that's just wasting its time creating and destroying particles. The difference is just staggering. It's not even a fair fight. So here's the bottom line. By designing an algorithm whose fundamental moves, these little particle hops, perfectly match the constraints of the problem, we don't just get a little speed up, we get a profoundly more efficient search that finds better answers with way, way less effort. And that leaves us with a pretty cool thought to end on. We took a concept straight from the real-world physics of quantum magnets, particle hopping, and turned it into an exponentially better algorithm. It really makes you wonder, doesn't it? What other amazing phenomena happening in nature all around us right now are just waiting for us to translate them into the language of quantum computing to solve the next big challenge?